in this chapter, we'll be studying the wave properties of particles. So particles which we usually think of as particles will now start to have wave properties. Okay, so the idea of particles having wave properties actually come from this person, Prince Louis de Broglie. Okay, so he's a French aristocrat, I think. So what did he say? He said that this is his statement being paraphrased. It's not exactly being mentioned like this, but this is sort of the idea that I get from his theory, the kind of vision he have towards the idea of nature. Okay, so he says that nature loves symmetry. So yeah, many things in nature works in a symmetrical manner. Okay, so he proposed something like this. He said that light is dualistic in nature, behaving in some situations like waves and in others like particles. This is what we have been studying in the previous chapter. We know that when we talk about light wave, think about it being able to undergo interference when we go through a double slit, or if you go through a single slit or a diffraction grating, you can undergo diffraction. So these kind of experiments are proving that light has wave properties in it. So it is because of it behaving as a wave that we can see this kind of interference pattern and diffraction pattern. Okay, but also if you learn about it, I think you've learned it in chemistry before, that you learn that light can be emitted or absorbed in the form of photon, especially when we talk about electrons moving from higher energy level to lower energy level. When they move from an excited state to the ground state, you learn that when the electrons fall into the ground states, the decrease in energy will actually result in the emission of a photon of light, okay, of light being emitted in particles, and we call those light particles as photon. Okay, so we see that when we talk about a certain scenario like diffraction or interference, we mention light to be behaving as a wave. But in certain scenario, when it involves something like absorption or emission, we usually talk about it in the form of photons, which is particles. So it shows that light has a dualistic nature, because in some situation it behaves like a wave, but in some situation it behaves like particles. Okay, so he says something like this. He says that if the nature is symmetric, so it means that everything works in a symmetrical manner, this duality should also hold for matter. Okay, so if light has a dualistic nature, then by the basis of symmetry, then matter, which is something very prevalent in our world, everything is made of matter, okay, should also hold this kind of duality as well. So he is proposing that if light that we usually think of as wave also have particles properties, so matters which are usually behaving as particles should also have the opposite thing, the wave properties. Okay, so this is the kind of symmetrical idea that he is trying to carry forward over here. He says that matters like electrons and protons, which we usually think of as particles, which is indeed particles, may in some situation also behave like waves. Because if light that usually behaves like waves can also behave like a particle, then electrons and protons that usually behave like particles maybe can also behave like waves. Okay, so this is the kind of proposal that Prince Louis de Broglie is proposing over here. And this kind of hypothesis or this kind of deduction we name as de Broglie's hypothesis, to say that maybe particles matter that we usually think of as particles might also have wave properties as well. So this is the idea he proposed, okay, but didn't really get proven by him himself. Okay, he himself just proposed the idea, he never really get it verified. It's someone else that managed to get this hypothesis verified. Okay, but now this is the idea of Prince Louis de Broglie. Okay, so now we are going to move on to talk about an equation that will relate between the particle properties of matter with the wave properties of matter. So one single equation will be able to relate between the particle properties and the wave properties of matter. Okay, to give you a rough overview, I'm going to introduce you some equations that are out of syllabus, but it's good to let you have a rough idea of how we talk about this kind of modern physics equations. Okay, so light, which we usually think of as wave, acts like a particle when it involves emission and absorption. So this is what we discussed just now when we talk about moving to excited states or dropping down to ground states, it involves an absorption of photon in order to go to an excited state, and involve emission of photon in order to drop to the ground state. So the change in energy level actually result in the emission or absorption of light, but in the form of particles, which we call it as photon. Okay, so by applying the idea of symmetry over here, we can probably say that matter, okay, which we usually think of as particle, will probably also will act like a wave. We also act like a wave when it involves some kind of situation. In this case, it will act like a wave if it involves diffraction. Okay, so the kind of proposal that he's saying that is that things like electrons, like protons, they are particles, but they might also have the ability to undergo diffraction because they are supposed to have wave properties. If you think of it, if you think of nature to be dualistic in nature. Okay, so particles like protons or electrons, which usually act like particles, might also have wave properties, and because of that, you might see things like protons and electrons able to undergo wave kind of phenomena, which for example, diffraction might occur for particles as well. Okay, so the general equation to talk about the energy of light or matter or these kind of things, it's this equation over here. Okay, don't worry too much about it. This is definitely out of syllabus. I'm just putting it here to let you see the big picture of things. So this equation, it's what you will learn if you learn about mass energy equivalence, those kind of stuff. Okay, but basically the idea is that this equation allows us to get two very important equations in physics. One equation is if you talk about light, the energy of light, because light has no mass, then therefore they are able to travel in the speed of light. Okay, speed of light in vacuum, 3 times 10 to the power of 8, is the fastest possible speed that can be traveled by anything in our universe. Okay, so because why light is able to travel at that speed is because it has zero mass. Okay, so we are going to assume photons to have zero mass, because only by having zero mass it is able to travel at the speed of light, which is the fastest possible speed. If light happens to have, or photons happens to have mass, then it will not be able to travel at the speed of light. Okay, but because light is traveling at the speed of light, therefore we can safely assume that light has zero mass, or the photons, the particle of light, does not have mass. Okay, so because light has no mass, the mass of light should be equal to 0, or the mass of photon is supposed to be 0. Then this equation, this first term over here will disappear. Okay, then you're left with square root of Cp squared. Then if you cancel out the square root and the square, you are able to get the equation E is equal to Cp. Okay, so if you are talking about light or you are talking about photons, then you can relate between the energy of the light, okay, which is just energy, and momentum of the light, which is something you might not be familiar with. Momentum is something that relates to mass times volume. Not mass times volume, what am I doing? Mass times velocity. Okay, when we talk about momentum, it's usually mass times velocity, right? So it's something related to something which is like a particle. Particle has mass, particle is moving, that's why it has mass as velocity, and multiply, you get momentum. But this equation is telling you that light, which has zero mass, can also have momentum. But in order to obtain its momentum, you have to understand this relationship in which the energy of the light will be equals to the speed of light multiplied by the momentum of the light as well. So the momentum of light is defined in a different manner. It is not mass times velocity, it is just taking the energy of light divided by the speed of light. Then you can get the momentum of light. So we are introducing some kind of interesting properties to light over here. So light over here has something called momentum, which is something not very closely related to something which behaves more like a wave. Okay, because when we talk about momentum, it's usually mass, something with mass, but here it is zero mass. Okay, so I'm introducing something a bit quirky over here. Okay, another thing that we can think about is matter. Okay, matter, we talk about light and matter, right? So if you are talking about matter at rest, if it's not moving, then we can know that the velocity will be equal to 0, right? So if its velocity equals to 0, the momentum should be equal to 0, because P is equal to mv for any kind of matter. Mass times velocity, velocity is 0, so momentum is 0. So if your momentum is 0, your second term over here will cancel out, it becomes 0. Then if you cancel out the square root and the square over here, you get the famous equation E is equal to mc squared. So E is equal to mc squared here, it's used to describe the energy, the rest mass energy of a matter, of something matter that is not moving. Okay, if it is at rest, that particular object or that particular matter over there, you can determine its energy is made of how much energy. The rest mass energy is made of how much energy can be described by this equation, E is equal to mc squared. So it means that if you manage to destroy this matter here to become no matter at all, how much energy will it convert to? It's a bit of an abstract concept, but the idea is it's called rest mass energy. Okay, so this equation over here actually encapsulates two important equations which we usually use to study modern physics. One is the relationship between momentum and energy of light. One is to determine the relationship between the mass of a matter and also the energy of matter itself. Okay, why do I introduce this equation is because I want to tell you that there's this equation E is equal to Cp, which is quite important. It's not in your syllabus, but it's something that is useful to our derivation. Okay, so now let's focus on light, which is the thing that behaves usually like a wave, but when it involves emission and absorption, it behaves like a particle. Okay, we know that the energy of light, according to what Planck has said and also Einstein as well, energy of light is E is equal to hf, because that is quantization of light. That is saying that your energy of a light is dependent on your frequency. The higher the frequency of light, the greater the energy of the light. Okay, let's don't go too much into the detail on that, but E is equal to hf, where h here is a Planck constant, which I will introduce later. Basically it's just a constant to relate between the energy of light and also the frequency of light. Okay, now I'm going to modify this equation here so you can follow carefully. I'm going to say that E is equal to Cp because I'm talking about light over here, so this equation can be used. So E is equal to Cp over here. At the same time, I'm going to say that because this is light, we know that light travels at the speed of light. So you can say that V is equal to f lambda, but the V, which is the speed of wave, we change it to the speed of light. So C is equal to f lambda. So we apply both of this equation to change this, to modify this equation here. We will substitute E to replace with Cp. We will substitute F here to be replaced with C over lambda. Then get Hc over lambda, which is something you might be quite familiar with chemistry, Hc lambda. So E is equal to Hc lambda. You learned about it in chemistry before. Okay, so on the left hand side you have Cp over here, and if you cancel the C over here, you'll get a very important equation for this chapter, which P is equal to H over lambda. So this is the equation for momentum. It can be used to describe the momentum of light. It is valid. So the momentum of light is taking the Planck constant, a particle constant, 6.63 times 10 to the power negative 34, divide it by the wavelength of the light. Okay, momentum of light is the Planck constant divided by the wavelength of the light. Why this equation is important, right? Why this equation is so interesting is because on the left hand side here you have momentum, which is usually associated with what we usually known as matter. Okay, because matter, it has mass, it has a moving velocity. So because of that, you can determine something called momentum. So momentum, this term is usually associated with matter. But wavelength over here is of course usually associated with light, which has a wavelength. We don't usually associate lambda here with matter. But now we are seeing that there's sort of like gray area, a gray area, or it's sort of like a crossover over here, in which light can also have matter properties, as it can also have particle properties as well, because it has momentum. Okay, it has momentum, so it behaves as a particle as well, so it has momentum. But this momentum here can be related to the wave properties of light, which is the lambda. Okay, the lambda represents the wave properties of light. The momentum here represents the particle properties of light. So this equation actually relates between the particle properties of light and also the wave properties of light. So this equation is very important. And in fact, because of the dualistic nature, we are going to say that matter here is going to apply this same idea over here. So for matter, we can also relate between the particle properties of matter, which is momentum, and also the wave properties of matter, which is lambda. We can relate them through this same equation as well. And this is the idea being proposed by de Broglie. De Broglie says that if light can have dualistic nature, why not for matter? Matter should also have dualistic nature. So the proposal is that if light, their wave properties and particle properties can be related by P is equal to h over lambda, then maybe matter can also have these same properties to relate between the particle properties and also the wave properties. So by knowing that, we can say that matter, we can determine its wavelength. So matter now has a wavelength. Matter behaves like a particle, but right now it has a wavelength. So how do we determine its wavelength? We can determine its wavelength by taking the momentum of the particle itself. We take the Planck constant and divide by it. So h over momentum, Planck constant divided by momentum, you get the matter wavelength. So now matter will be associated with a wave properties by having a wavelength. Okay, so of course you know that matter momentum is P equals mv. So you can shuffle a bit of equation. Then you can have the de Broglie's wavelength or the matter wavelength to be equal to h over the momentum, which is the mass multiplied by the velocity of the particle. Okay, so right now by saying this, we can say that matter has wave properties and particle properties because matter now has a wavelength which represents the wave properties of it, and also a momentum to represent the particle properties of it. Light also have wave properties and also particle properties. The particle properties is represented by the momentum over here, and the wave properties is represented by the wavelength over here. So this important equation here shows the relationship between the particle properties and the wave properties of light and matter. I would like to mention again here what I've written down over here. It's all out of syllabus. It's just for me to let you know the context of how we get this equation P is equal to h over lambda. It actually comes from knowing by having an understanding of how light behaves as particle. Then from there we say this same duality over here can be brought over to matter. Okay, so we get this equation by studying light, but we say that because of the dualistic nature, maybe this equation can also be used for matter, and it turns out to be true as well. Okay, so the whole thing over here to understand how we derive the equation is actually out of syllabus. You just need to know that for matter, you can relate between the particle and wave properties by using P is equal to h over lambda. You don't need to worry too much about the derivation. It's just to let you see the context of how everything comes into shape. Okay, so that's it for now. In the next video, we move on to talk about a setup to prove this equation P is equal to h over lambda, or to prove that matter has wave properties. So we'll be studying the Davison-Germers experiment in the next video.